Alright, so we're gonna start a new series, and this one is about the number series. The number series is about finding the divisibility of the numbers and finding the remainder, just for the sake of finding the relationship of different numbers and different properties. And the book we will be using is the second edition of Elementary Number Series by Underwood Dubly. I don't know how to pronounce the name, I'm sorry. And today is the first episode, and we will be going through the exercises of this book because a lot of the exercises in the end of the chapter, they really don't have the answer. Even if they do, they don't have the process of how they get the answer, and sometimes it is very confusing. That's why I hope to make this video to show you guys how did I solve those problems if you just really struggle and don't know how to do it. Yeah, we all have been there before, and that's why I'm making this video. Although I'm not able to solve 100% of the question from this book, but I say around 90%, and this is a very good amount. And yeah, we have been talking about this for a long time now, so let's officially begin. And we're gonna talk about chapter 1. So the first question is about finding the greatest common divisor of the two numbers. And we have learned the Euclid algorithm earlier in this chapter. And we're gonna go through this as an example. So the first one is 714 and 159, and how it works is that you have a bigger number here and a smaller one, and you take the remainder of this when divided by this, and you get 150. And then for those two, this is one is bigger, this one smaller, you take the remainder of this one when divided by this, you get 4, and you just keep repeating this process. And at the end, when you see the number 0 and the other number which you have, it's going to be the greatest common divisor, and in this case is the number 1. And just similarly, you take the remainder of this when divided by this, and you get this, and you take the remainder of this when divided by this, we got this. And now when you divide this to this, you get 0, which means 592 is the greatest common divisor, and that's how we get our answer for those two. And yeah, to avoid too much repetition, we are just going to do some of them. I'm not going to do those two because it's a little repetitive, and I don't know, the way I'm talking is kind of repetitive too. So just check your work, alright? This is the answer. And let's go to the next type of the question. So we are given a linear equation, and we're gonna find one of the integer solution. So for the step 1, we're gonna still using our Euclid algorithm, and we start at the bottom now instead of at the top. So 1 can be represented by 4 and 3. And when you are doing the reverse Euclid algorithm, you start with the bottom and you try to represent those lower numbers by those higher level until you reach all the way to the top. For example, 1 is represented by 4 minus 3, and this 3 can be represented by 155 minus 4 times 38. And then we simplify a little bit, and we combine those 4 together, we get 39. And yeah, we take out the 155, and 4 we can represent it by 159 minus 155, and don't forget to time this for 39 over here, and then we factor out and we get this. And just similarly, we represent the number 155 by 314 and 159, and we factor this out, and after a few shuffling we get 79 to be the value of y and negative 40 to be the value of x. And if you really sub in this into the original equation, you should be getting 1. And for number 4, it's just the same problem. And when you are trying to do those things, you really want to simplify this by dividing the common divisor of those 3 numbers, which means we divide 592 for this, and for this before you do the reverse Euclid algorithm. And this one you should get x equals to negative 11 and y equals to 6. And let's go to question number 5. We are going to prove the greatest common divisor of n to any of those 3 numbers a, b, c. They should all be equal to 1. And the reason why it's simple, because n minus abc, yeah, we take the abc here to the other side, and we get n minus abc equals to 1. If those 2 numbers, they do share some kind of factor, let's say d over here, and this is an integer, and d is also an integer, that means that d is a factor of 1, which means d could only be 1 because d is positive, obviously. And that says that n and abc, those 3 numbers, they do not share any factors. So that's how we get those 3. Their greatest common divisor is equal to 1. And next question. Okay, now we are asked to find 2 different solutions for a linear equation. There's really nothing to talk about. We first get the greatest common divisor by using the Euclid algorithm, and then we do a reverse Euclid here, and then we get one of the solution. How do we find another pair? Is that if you observe this, the slope of this is 23 over 19. Okay, negative 19, because as for every 23, y increased and x is going to decrease negative 19. That's how we get a slope. And yeah, plus 19 here and divided by negative 23. So we get another pair of solution. And let's take a look at the next question. So question number 7, prove that if A is a divisor of B and also B is a divisor of A, then either A equals to B or they are the opposite. So for a number to be the divisor of another number, that means the absolute value of the divisor should be less than the original number. I think that's very easy to understand, right? So we got those 2 interesting relationship, and from those 2 we combine, we get the absolute value of A equals to absolute value of B, which implies those two relationships, and that's what we are trying to prove. And the next question, number 8, if A is a factor of B, then A is greater than 0, then the greatest common divisor of A and B equals to A. So, we know that if A is a divisor of B, then B divided by A, this is some kind of integer that we don't know. And the 1 and this number here, their greatest common divisor is 1. I think this is very easy to understand. And we multiply this and this and this by A. We get A and B. Their greatest common divisor is A. And that's what we are trying to prove. And next question. So question number 9 here. Prove that, okay, this is ugly. So suppose A and B, they have the greatest common divisor as D. And that means that D is divisible to A and B. D is a factor to both A and B. And we know that B divided by D is some kind of integer because D is a factor. And they are the greatest common divisor is equal to 1. And we multiply both sides by D. D and B, they have greatest common factor of D. And we substitute D for this one. And now we have this ugly expression. Great, we solve it. Yay. And next question, number 10. Prove that n and n plus 1, they share no factor other than 1 for all n greater than 0. Okay, let's say they share some kind of factors named D, and we know that n plus 1 minus n equals to 1. If those two, they do share some kind of factor D, and we know that this is integer, this is integer, this whole thing inside this square bracket is an integer, and D is also an integer. So D is a factor of 1, and D is positive, that's why D equals to 1. And they share no factor other than 1. Great. Part B. So what could n and n plus 2, the greatest common factor, be? So it could be 1 or 2. One example, for example, 1 and 3, 1. N equals to 2, they share a factor of 2. This is just an example, so nothing much to it. And question 11. So prove that if k and k plus k, they have greatest common divisor of 1 only if k and n have greatest common divisor of 1. So for this one, we're gonna just jump right into part B, because once you solve part B, A is also be solved. So the conclusion for this one is true. The reason why is because if A and n plus k, they share any factor of D, you find this is an integer, and n plus k is an integer. We already know that this is integer. Since this and this is integer, then their difference should also be an integer. So this and this, they are also integer. And D is the greatest common divisor. That's why n and k, they share a factor of D. And if we have n and k, they share a factor of D. This is integer. Those two are also integer. This is also an integer. So they are going to share a factor of d, and d is the greatest common divisor. So when they say if and only if, that means like if you work this the normal way and the way that's opposite, you work the way the other way around, it should give the same thing. Like you work this normally and the other way around, they should, like the two things, they should be interchangeable. And yeah, let's go to the next question. So question number 12. Prove that if A is a divisor of B and C is a divisor of D, then no, sorry, A is a divisor of B and C is a divisor of D, then AC is a factor of BD. So we know that this is an integer, this is also an integer, then their product should be integer, and this is their product. Yeah. And question 14. Sorry, 13. So D is a divisor of A, D is also a divisor of B, D squared is a divisor of AB. Well, I say it's pretty similar to last one, and yeah, those two are integer, this is integer. That's it. And question 14. If C is a divisor of AB and CA has the greatest common divisor of D, then C is a divisor of DB. So suppose A is equals to DK, and as we know, and D is a divisor of A is yes, C and A, their greatest common divisor is D, and D is a factor of A, and the other part is K. Then since DK and C, the only common divisor is D over here, once we cross that out, then this K is pretty much useless. We can just get rid of that. So DB over C, this should be an integer. And this leads us to the final question of the day. And this one I personally think is a very challenging one, and although not being stated explicitly, but I assume that A and B, they are some kind of integer, although they did not mention that, but I think that's how you should work it. How you gonna solve the problem. You're gonna assume that A and B, they are some kind of integer. So before we jump into the question, we gonna introduce a little formula over here. For any quadratic equation ax squared plus bx plus c equals to 0, we know that root formula is this: x equals to negative b plus minus square root b squared minus 4ac over 2a. If you multiply the two solutions, you get c over a. If you plus the two solutions, you get negative b over a. That's very important. And by using this formula in this case, go back to the x squared ax plus b equals to 0. Yeah, we get the sum of the two solutions equals to negative a, which is an integer. Suppose x1 is the integer solution, and then we're gonna find x2 equals to this ugly thing here, which is also an integer. So we know x1, x2, they are both integer, and b is also an integer, which means x1 is a divisor of b, and yeah, x1 is divisible to b. That's what we're gonna prove. That's what we were going to prove, and we prove it. Good job. And for part B, if it has a rational root, show that this. Okay, welcome back. So part B, we know that it has a rational root. We have to show it is in fact an integer. Still using the sum formula over here, we got x1 plus x2 equals to an integer. Suppose x1 has a form of like this, a fraction, and x2 equals to this, and b is still a product of the two solutions. And also those b is an integer, and the x1, x2, their product should be an integer too. So this is an integer. When you're expanding this out, we know that k1 is not able to divide the whole p1. That means probably that there will be some factor of p1 being left, and that left part of p1 along with the other p1 factor should be a divisor of this part. Because we already used all we can over this side, we can only use this. Therefore p1 is a divisor of this. But we will find that we got this is an integer. This is of course an integer. This should also be an integer, which is contradicting our original assumption. Which means this is impossible. That means p1 is indeed a divisor of k1, and x1 equals to k1 over p1 is an integer. And that concludes our section for chapter 1. I hope it could be helpful this video turns out. And see you in the next one. Hopefully I could have next one and didn't quit my theory. Yeah, that's it.